Tell the operative first line of that, right?
That's, well,
Yes.
I will, because that song was the lullaby that I was brought up with. And I never actually, I mean, she sang the first verse, which you heard about 10,000 years. And I never made the connection between the 10,000 years and that was the lullaby that I was sung until Hazel saw the clock, and that's immediately the thing that she started singing it. So I don't know if that's where 10,000 years came from for me, but it might have been. This is a funny talk because actually a lot of the people in this audience have kind of been involved in this project from the very beginning. And I see a lot of my collaborators and supporters and donors to the project and the people that encouraged me to do it in the first place. So for them, this is kind of a progress report, but I know also a lot of the audience doesn't know what the hell I'm talking about here, and doesn't know what that object sitting out there is. So if you'll bear with me for a while, I'll just catch everybody up a little bit and give them the history of this 10,000-year clock project. Almost 10 years ago now, I had a little high-tech company, and I was working on a project to build the fastest computer in the world. And I was really obsessed with kind of speed and nanoseconds and picoseconds, and all my customers were obsessed with speed and doing everything faster, 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 and trying to get product cycle times faster, and everything was about speed and fast, and it seemed to be accelerating. And sort of in the middle of all of that, Stuart Brand told me a story. He was doing a book on architecture, and he told me this story about a building in England. It was actually the common room of New College, Oxford, that had been built in the 15th century. And this building was constructed out of these 40-foot long oak timbers, which were easy to get in the 15th century. But sometime in the 1950s, they were doing a renovation of the building and updating the electrical. And they discovered that the oak timbers actually needed replacing. And by then, you couldn't just go down to a lumber yard and buy a 40-foot long oak beam, because oak trees of that size were long gone from Europe for the most part. However, Oxford University owned some forests, so the people that were doing the renovation called up the Oxford forester and said, you know, we're from New College, we wonder if you have any big oak trees. And the forester basically said, oh, we've been wondering when you'd call. We've had those trees that we planted 200 years ago to replace the oak beams in New College when they needed it. And when I heard that story, the idea that somebody would plant an oak tree with the anticipation of harvesting the oaks a century later or whenever it was, I realized that that was a kind of thinking that was just so antithetical to everything that I was doing and everything I was spending time with. And I felt like I was missing something in my life because of that. And when I started thinking about it, I realized that even during the course of my own lifetime, people had gotten sort of shorter and shorter in their point of view about the future. And that when I was a kid growing up in the 60s, people really thought about the year 2000 as a real year, and they were really kind of planning for it and tried to imagine what it would be like and sort of had visions of it and so on. And it was getting into the 90s, and people were still sort of thinking about the year 2000 and what it would be like. And here it is 2000, and we're kind of thinking about the year 2000 and what it's going to be like. So it's like the future is shrinking. And I realize part of it is, I think, this whole mental barrier of the millennium. So I've been really looking forward to getting past this whole 2000 thing, because I think it's been a big mental block for us of feeling like we were at the end of something. And now I really do feel like it's starting to feel like we're at the beginning of something. And suddenly we've got this big sort of blank sheet of paper out in front of us that we can do anything we want with. And I think you can even sort of tell, it's kind of an undertone of a lot of the talks that you've had here at TED, of people just sort of stepping back, trying to rethink a little bit, you know, what are we going to do with the opportunity? We've got a fantastic situation here, we've got amazing resources. What can we do with it that is going to leave the world a better place? What are we going to do with this next century, with this next millennium? And as I started thinking about that, this was, again, back in the early 90s, I realized that what I wanted to be doing something like planting acorns. I really wanted to to be thinking out in the future. And one of the things I started talking about, just as a kind of, it started out really just as a story, as I started saying to people, what I'd really like to do is build a clock that lasts for 10,000 years. And that, imagine it sort of up on a mountaintop someplace, and the people would just know it was there, and they could go up and kind of wind it once a year, but they would know that they were sort of participating in something that would continue for a long time. And I guess it's just because I'm an engineer and I sort of approach these things by what can I build. But it became an image that kind of stuck in my head, and I found that as I talked to different people, it would resonate with them, and it would get them thinking, and they'd start thinking about different things, like who are the people that take care of that? Where do we put it? We can't put it in a city. Will the city really last for 10,000 years? And it started getting people thinking, and the more I talked to people, and it's actually mostly people that are in this room that I talked with, the more the project became real to me, and I would I would literally wake up in the middle of the night, be kind of thinking about this clock and how to do it. And after a while, I realized, I'm really going to build this clock. So what this is now is this is kind of a progress report. What's out there is a model, it's an intermediate model of what's going to be a much larger clock up on a mountain someday. And I'm going to take you through and just give you a sort of quick overview of what it is. And then I think what I'll do, I don't have time today really to explain in detail all of the things about the clock. But I thought what I'd do, because working on the clock has been for me, boy, this term's gotten used a lot, but it has been for me, something that's changed me. And it's been a transformative experience for me. I've looked at things differently working on it. So I thought I'd just take one little tiny piece of the clock, so tell you what it was like to work on that, sort of the thinking that went into it, and tell you a little bit about kind of how it changed me and how it changed how I look at the world. So let me first start. We've got a video camera outside in the lobby. And this is my collaborator, Alexander Rose, who's actually working full-time now. He's the director of the Long Now Foundation, which is the foundation that's building this clock, and now doing a number of other long-term projects, like making a long-term library that lasts for thousands of years and so on. And Alexander's going to be kind of the Vanna White pointing at the clock, but you should also, if you have questions about the clock, he's a good person to ask. So first, let me just start with the face of the clock. That basically, one of the problems with the clock is in 10,000 years, what do you put on a face that's meaningful to people over time? So one of the things I did is look back at things that are meaningful to us that have lasted a long time, like Stonehenge, like Mayan calendar stones and things like that. And it turns out the thing that we can connect with most is the thing that stays constant, which is our Earth, the stars, the sky, and so on. In fact, every culture counts years, months, and days. There are other things like hours and weeks, which are very particular to our culture. But actually, just stay on the clock for a moment. So if you look in the center of the clock, what you see is a field of, If you look in the center of the clock, what you see is a field of stars. And that's a kind of astrolabe. It's like that planisphere thing that you buy in the Science Museum that tells you which stars are showing in the sky. And that actually rotates during the course of the day, the sidereal day, and also rotates, as I'll explain later, over 26,000 years to show different stars at different times. So that shows what the star pattern looks like. And also, above that, you'll see the sun. If you can just move the camera up a little bit. And that actually shows the position of the sun in the sky. And when the sun comes down lower, you'll see that it actually would cross the horizon there, so that it would go under the horizon. So you can tell sunrise, sunset, what time it is. And similarly, the moon is displayed there. And you can see where the phase of the moon, and you will also be able to see whether the moon, right now the moon is below the horizon. So that's the basic part that could connect over a long period of time. The only numbers on the dial, the only thing that shows is the year number. So it shows 2000, or actually what it shows is O2000, because of course this is a Y10K compliant clock, and it has to have. And actually there was a moment of great relief a couple of months ago, because it turns out that we actually got this prototype of the clock working at about 11:30 p.m. on January 31st. And we hadn't tried it. And of course, we had invited a lot of friends over to see it and things like that. So we got it working, we got it ticking. And there was a really high tension moment there when 12 o'clock came, but sure enough it switched from 1999 to 2000. And then there were these two beautiful bongs as it struck 2 for 2000. So if I just show some of the other parts, this part here, the way that the clock is powered, that was another big puzzle. When I first started this, I sort of approached it as an engineering problem and designed all these great ways for the clock to be self-winding by temperature change or by the occasional earthquake or all kinds of things like that. And I realized it's all silly, that the real thing that matters about the clock is whether people care about it. And in some sense, why should people care about a clock that doesn't care about people? And so I realized the right thing for the clock is to have it wound by people. So in fact, the clock is designed to be wound once a year. And the spirals up there turn around and lift up those weights once a year, and then the weights fall and twist it, and that's what powers the clock. Now if you go and look below the clock at the very bottom, you'll see, if you move the camera over to the pendulum, you'll see a very slowly moving torsional pendulum. Those are 3 tungsten balls. And a lot of the reason the clock is able to last for so long is that it moves very, very slowly. So it only ticks the same number of times in 10,000 years that an ordinary wristwatch would tick in 100 years. So things don't really wear out that much. So this pendulum has a period of about 60 seconds. And it should be exactly 60 seconds once we get it tuned up perfectly. And that is the basic timing of the clock. Now that's not really accurate enough to keep the right time for 10,000 years. So the clock actually has another unit on it, which we didn't bring down because it's not really it's not machined to the same standards yet. But it's a unit that has a lens in it that synchronizes the clock with the sun, so that when the sun is directly overhead, it knows that it's solar noon, and it adjusts the clock forward or back to sort of keep it synchronized. So as long as the clock gets a sunny day once every few years, it will manage to keep the right time. This is the escapement of the clock, and actually if you move up a little bit, just point out where the equation of time cam, which I will talk actually quite a bit more about, which is that curvy thing in the background. That's the thing that keeps track of the relationship between the solar time and the clock time. I'll talk more about that later. But if you go down, the bulk of the clock down below is essentially a computer. It's a mechanical computer. In fact, you can see the bits in the computer. If Alexander, if you'll point to a bit, those little levers that are sticking out, those are bits. And depending on whether they're in or out, they're a 1 or a 0. So when the clock ticks every hour, what it will do is it adjusts those, and a kind of mechanical adding machine actually calculates the new positions of the dial. In fact, Alexander, if you can just sort of force it to tick so that we can sort of see the computation take place. It's something that normally just happens on the hour. But if you see that sort of sliding that's happening in there, that's basically, you'll see some of the bits beginning to change position as it slides by. That's the way that the computation happens. So it's a clock. It's actually a 28-bit computer with a cycle time of 1 hour. So it's the slowest computer in the world. So one thing to remember about this clock is this is really just a working model. It's a small-scale model of a clock that's intended to be much bigger. So this is our first working prototype. And in fact, well, I'll explain in a second, but probably the next one will be actually twice the size. And then eventually there'll be one twice the size of that, and then eventually we're going to put one in a mountain. In fact, if I can just switch to the slides at this point, let me show you. We just bought this year the mountain that we want to put it in. This is a solid limestone mountain in eastern Nevada. It's about as far away from any city as you can get in the United States. It's basically equidistant from Salt Lake City to Reno, Nevada to Las Vegas, kind of in that triangle. And there's going to be a clock basically 10 times the size of the model that you see buried into that mountain. It's in the White Mountains. It's surrounded by national park, actually on all sides. It's a little private piece of land in national park. But the reason that we loved this piece of land and picked it for the clock is these trees that are up in it. And let me just give you that last picture for scale. I can go back to it. Those trees in the background that Alexander and I are on, that's a 5,000-year-old tree. It's been growing for 5,000 years. And actually the log kind of in the background is probably another 5,000 years worth of tree rings. So there's kind of 10,000 years worth of wood lying around in the trees. These are the oldest living creatures on Earth. And these forests, just to give you some sense of it, this tree, for instance, was 1,000 years old when people started building the pyramids, and is still alive now. One of the things that I've started realizing about the clock, from building the clock, is my sense of time has really been kind of changed by it. And I really don't think of 10,000 years as being all that much time anymore. And just to give you a sense of what 10,000 years is, 10,000 years is actually about 400 or 500 generations, which is about the number of people that are in this room. So if you'll imagine for a second that you all are my ancestors, and you sort of represent those 10,000 years worth of ancestors. This is how many they are. Imagine you're sort of arranged in order. So the people on the back row are the ones that invented agriculture. And kind of here in the middle are the people that built the pyramids, and the first cities are a little above them, sort of right over there. And maybe these 10 people right here are the ones that invented everything from steam engines to electricity to computers to penicillin to the internet, all squeezed right into this little front row here. And once you start thinking about what a clock actually has to do, you realize that this 10,000 years is really it's a very human time scale. We actually have artifacts that are that old. We have pots and baskets and things. There's really technology that's 10,000 years old. So it's actually very plausible. And I just visited a wooden ship that's in perfect working order that's about 4,000 years old. It's very plausible that out of good materials we should be able to build something that's 10,000 years. It's a believable amount. So I thought that what I'd do, rather than try to explain the details of the clock, is to pick one part and sort of tell you what it was like to design it and sort of the thinking that went into it. And I really had trouble because there are a lot of parts that I love in the clock. One of them that I almost did the whole talk about was just the pendulum bob, which is made of tungsten, and the exact size of the ball and the ways that the holes are drilled and things like that would actually tell people a lot about our culture. And this is made of one of the densest materials on Earth. And actually what I'd like to do rather than explaining is I'd like to just pass it around. Be very careful with it, not because you have any chance of damaging it, no matter how hard you try, but it might damage you. In fact, we give those to our big donors, get them, and it comes with an instruction sheet that says, please keep it away from plasma torches, direct blasts of nuclear weapons, as these will cause unsightly surface blemishes. The other part that I really seriously considered talking about was the way that the mechanical computer worked. And I was going to talk about this part, which sort of encodes the idea of binary arithmetic, and really which is kind of the key idea in modern digital computers, because that's the way that the clock does its computation. And I think that's probably a little bit too complicated thing to do right now, but I did have a great moment yesterday explaining this to Andy Grove and sort of showing him my microprocessor. And the best moment was when I explained to him that every 18 months I plan to have it get twice as big, twice as slow, and twice as expensive.
Moore's law.
The part that I'm going to explain is this part, which was, I pointed out to you, is the equation of time cam. It solves a very specific problem in the clock, which is this relationship between solar and clock time. And I actually took very seriously that this conference is about understanding. So this is I figured I had to teach people at least one thing that they would remember in all of this. So I'm going to clear up one of life's little mysteries for you, which is, what is that figure 8 floating in the middle of the Pacific? It's called the analemma. You've all seen it on your globes. And it's to help you solve a certain problem, which was actually a big deal before mechanical clocks. And the problem is this. The sun, you've probably been told that the sun is overhead at noon. Well, it turns out not to be exactly true. The sun is about overhead at noon, but where it actually is really depends on the time of year, and actually it depends on which year, as we'll find out later. But if you took a picture, if you put out a camera and took a picture of the sun every day at noon, or let's say the first day of the month, this is actually a picture that was done that way. I can go. This is an amateur astronomer did this. And you see the photograph, and you will recognize exactly that same figure 8. It turns out that, sure enough, at the equinox, which is right there in the center, it is directly overhead. But sometimes it's a little bit advanced or retarded depending on the time of year, and of course it goes up and down in the sky from winter to summer. So the clock, because it synchronizes on noon and tries to get its idea of 12 o'clock, it has to know about that function. But it turns out that there's another problem, if you're really thinking about this over 10,000 years, which is the Earth, you all know, is sitting here spinning like this, and it's going around the sun over the course of the year. But there's another motion, which is called the precession, which the Earth is actually wobbling like this. We don't notice it much because it wobbles once every 26,000 years about. So in fact, right now, it's wobbled in such a way that it's pointing toward the North Star. But in fact, in 10,000 years, what we call the North Star, Polaris, won't be any place near the North Pole. In fact, Vega will be the North Star. So in fact, the star field changes. And the clock, that star field in the center of the clock, does rotate around once every 26,000 years in that right way to show how that changes. So an archaeologist could actually look at it and sort of set the date correctly just by getting the stars in the right place. But the other thing that happens, though, is that figure 8 shape actually changes shape as the thing wobbles. So it changes shape over 26,000 years. So somehow I had to have the clock not only know that figure 8 shape, but know how that figure 8 shape changed over that much time. And just to give you an idea of sort of what the process of design is like, all of this starts out, I guess started out by doing a lot of reading about astronomy. And interesting enough, a lot of the ways we know how this is changing is from very old calendar systems like the Mayan calendar system. And so I got to read a lot about old Mayan calendar systems and so on. But in the end, the result of all this reading was kind of pages and pages of sort of math that I had accumulated from these. And so it sort of got reduced to some point where it looks like this. And this is partly because Nathan Merville dared me to put up an integral sign at TED. But you have this kind of junk, which I certainly can't look at and tell what kind of shape that's going to be and what that's going to look like. But it does sort of explain what that relationship is over time. And then you have to figure out how are we going to take that relationship and put it into a mechanical device. And so there's some obvious ways of doing this. One of the most direct ways is you basically cut a piece of metal whose height is equal to that mathematical function, have that piece of metal rotate around. And so I sort of plotted out what that shape was going to be. And I ended up with this, which sort of looks like a 45 RPM record that somebody left out in the sun too long. But this really does the job. And in fact, it's a very good mechanical way of solving the problem. Now, had this been sort of a straight engineering problem, I probably would have stopped right there, because as engineers, we're sort of trained, you define the problem. As Brand said, you're requirements driven. I had met the requirement. That solves the problem. And in kind of any other engineering project I've ever worked on, once you've got a solution to the problem, you stop and go into the next one, because time is you've got the product cycle times are important and so on. But this project was of a different sort. And so I had a chance to come back at it a different way, and I wasn't very happy with that. It just didn't do anything for me. And I came back and I thought, well, maybe instead of doing it as a disk, do it as a cylinder. I ended up with a shape like this, which also is kind of more interesting, but frankly didn't thrill me. So I sort of had the luxury of I didn't know what to do. I was a little stuck, and I just went away from the problem for a while, which is, again, something you just can't do in a normal engineering project. And then suddenly hit me that I'd actually parameterized the whole thing in terms of calendar years, which were this obvious false construction, and that really what I should do was parameterize it in terms of astronomical years, of which there's a various type. And I sort of went in and I adjusted the equation, and the first plot that came out was this one. And I suddenly, as soon as I saw this, I knew that I had found a new friend. I mean, this was right. I knew I didn't have to go any farther. I really loved this shape. And so in fact, that shape is in the clock, and this is the way it works. This thing turns around once every calendar year. And then over the course of 10,000 years, an arm goes up, and you can see it on the clock, and it slides up here over the course of 10,000 years. So this is sort of 10,000 years of time that I'm holding in my hand, and I think it's a very beautiful shape. So I started thinking about that, and I started realizing how different this was from any other engineering project I'd been on. I realized that so many of the things that we're building right now, we just have to we're under such speed pressure, and it's sort of the right thing in a corporate environment. You really just want to get to work, you want to get out there. And I started realizing that almost all of our technology that's produced out there that we're using is really just stuff that was kind of shoved out the door as fast as possible. And it got frozen into various states that we're sort of putting up with. And if I think about technology, basically, my definition of technology is the stuff that doesn't really work yet. And I think that's kind of literally true, because the forces of economics that sort of drive technological innovation, technological production, sort of encourage the fast mover. So it's almost never the one that you stopped and thought about in the sort of third version and got it right and so on is the technology that's out there. So you end up with a technology that's sort of the equivalent of that first record plate that sort of solves the problem, but it sort of doesn't solve another problem that could have been solved. And so increasingly, I guess, since I've been in this project, when I look at everything out there, it feels like almost we're in a state of 100% sort of alpha test on everything that we're working on. And I see very few people stepping back and doing the kind of thing like Bill Joy was doing yesterday. I'm starting to look at all this stuff and say, well, this is how it came together, but how should it have come together? You know, what rules should it have, you know, let's step back and do that. And I guess I'm optimistic that we're going to be able to do that. And I guess one of the ways that this project has changed me is I'm going to do that. That's a piece of what I want to do, is sort of step back and try to get out a little bit of that race of what can I get out the door the fastest, things like that, and try to step a little bit of how things should be organized. How should we make all of this work? Because I think we can make it come out very different. But in any case, whatever I do, I'm going to continue working on this project for a long time. I hope I'll get chances to continue to give updates on it. Maybe TED 20, I'll show the big version of the clock or something.
10,010. What happens after 10,000 years?
That's a good question, and we're still talking about it. Now, I'll answer those questions. I mean, I know I'm out of time here, but I just wanted, since so many of you have helped with this project and made it possible, I just wanted to thank all of you for giving me the opportunity to do this. Thanks a lot.
The gentleman who is passing out the balls is one of my heroes. I've introduced him that way at TED. I'll say it once again, Stuart Brand. Such a rare presentation, such a rare thing to do. I mean, it's really rare. Rare to take an idea and to want to solve it so absolutely. You know, somebody defined religion as ultimate concern, and this is kind of an ultimate kind of idea. It's a very special thing. It's really a special thing. young people use the word awe and awesome too much today, but so it doesn't have the meaning it used to have. But I'm really in awe of something so complete. There's a term in physics called, they call things an elegant solution. And it doesn't mean Gucci elegant. It has a different term. And they also have terms called charm. And this is both a charming idea and an elegant solution. It's really, really, really special. And this is a moment. This is a moment to see this first semifinal model and hear at least part of it explained. And I don't know, I think it's real special.